Okay, good morning. Be welcome to the online edition of the Astrobiology School at Observatório Nacional. My name is Marcelo Borges Fernandes. I'm the head of the graduate program in astronomy of the Observatório Nacional and also a member of the organizing committee of the Astrobio Online. So let me tell you a bit about the history of our astrobiology school. So since 2014, we have our biannual astrobiology school, but due to the pandemic of COVID-19, in the last year, we could not organize the fourth edition of Astrobiome. So this year, even with the continual restrictions due to the pandemic, we decided to have a more compact version of Astrobiome, an online edition called Astrobiome Online. So if the sanitary conditions allow us, I would like to announce that next year we will have the Astrobiome in its traditional face-to-face format. We will keep in format, okay? So please, turn on. So before we start, I would like to say thank you very much to all the professors for accepting our invitation to be a lecturer in the Astrobiome Online, Dr. Adriana Valio, Dr. Janet Siffert, Dr. James Casting, and Dr. Mario De Pina. And also thank you very much to the organizing committee, Dr. Beatriz Siffert, Dr. Gustavo Porto de Mello, and Dr. Renato Dupke. Thank you to the team, our computer division, and also a special thank you to the Division of Education and Outreach of Observatório Nacional, especially Josina, Lorena, Eugenio, Rodrigo, Vanessa. Thank you so much for all support. And now some important information for you attending the Astrobio Online. After the presentation, there will be time for questions for people here at the Zoom. For people at the YouTube, please write your questions in the chat. It can be in English or in Portuguese, and your questions will be read by us to the lectures, okay? And second, and very important, we will share in the Zoom and YouTube chat a link for the attendance list for those who want or who need a certificate. So please pay attention because there will be a different link for each lecture, okay? So you just need to click on the link, fill the form and submit it, okay? Each list will be available up to 10 minutes after the end of each lecture. So please don't forget to include your name and also your email in each list for each lecture, okay? So I think I talked too much, so I would like to invite, please, Dr. Beatriz Siffert to introduce our first lecture, okay?
Thank you, Marcelo. Welcome, everyone. Good morning. So our first lecturer is Professor Adriana Valio. She received her physics degree from the State University of Campinas, Unicamp, her master's degree in astronomy from both the University of São Paulo and UC Berkeley, from which she also got her PhD in astronomy. As a postdoctoral fellow, she worked at Unicamp and Caltech, and she's currently professor at the Center for Radio Astronomy and Astrophysics at the Mackenzie University in São Paulo, and she's the coordinator of the graduate program in sciences and geospatial applications at the same university. She holds the title of Livre Docente at the State University of São Paulo. She has occupied the positions of chair, treasurer, and secretary at the Brazilian Astronomical Society, and she's a member of the Physics and Astronomy Advisory Committee at our National Council for Scientific and Technological Development, CNPq. And she also holds the current she's also the current coordinator of the astronomy section of the São Paulo's Research Foundation, FAPESP. She has experience in the areas of solar and stellar activity, exoplanets, and their interaction with host stars and habitability. So thank you, Adriana, for accepting our invitation. You can start whenever you want. Thank you.
Okay, well, thank you, Beatriz, for the introduction, and thank you, Marcelo, and all the organizers for giving me the opportunity for the invitation and giving me the opportunity to talk a little bit about, well, the astrobiology and its implication to, to impact, especially on the impact of stellar activity on the habitability of exoplanets. So I'll, besides giving an introduction to the subject, I'll also talk, especially in the second half of the talk, a little bit about the research that I have been conducting together with students and ex-students. So before we start about talking about the impact of stellar activity, I would like to characterize what do I mean by stellar activity. Stellar activity can manifest itself in the forms of spots, flares, coronal mass ejections, and also a stellar wind. Of course, all these phenomena are associated with convection, magnetic fields, and stellar rotation. So, and as we'll see throughout the talk, I'll always make a parallel or an analogy with the solar case. So, sunspots. It is well known since the 1800s that the number of spots, which are these dark regions on the surface of the sun, they vary in number through time, with a period roughly of 11 years, which is also known as the solar activity cycle. And here is a plot for the last century, for the 20th century, of the variation of the number of spots. And an interesting thing is that if you also measure the solar irradiance, or that is the brightness of the sun, and of course this measure is done from space, through various spacecraft, what was noticed was that when the sun had had more sunspots in its surface, it also was a little bit brighter, just a little bit, like about 0.1%. And people, to understand, because that was initially a paradox. Well, if there are more dark regions on the sun, why is it brighter? Well, it's brighter because not only the sun has on its surface the spots, which are indeed the dark regions here, but there's also faculae, which are bright regions. They're magnetic tubes with hot walls. And these you can see here as this white regions, which, they're smaller, but they occupy a much larger area on the solar surface. Thus, it enhances the solar brightness. Not only the sun present solar activities, not only the sun present activity cycles, other stars also present. And here is just an example. Well, here is throughout the years, and this is the same time period from 1965 through 1995 of the sun and other three stars, showing a periodic variation in their emission. And here are some more examples. And this was known as the Mount Wilson sample. And what Sally Baliunas found, in the Mount Wilson program, which observed many solar-like stars, especially in the lines of calcium 2, H and K, and was that 60% of the stars presented periodic activity or cycles. 15% were variable but without any obvious periodicity, and 10 to about 15% were non-variable, which here are some examples, or were like in a quiet state. For the sun, we know that there is a dynamo mechanism in action, which was explained by Parker in 1955, the alpha omega dynamo. And basically, this is also known as the Babcock cycle. And basically what happens is that the magnetic field lines, which are generated in a very thin layer between the convective zone and the radiative zone, at this interface, there's a layer called the tachocline, and this layer, there is a strong shear of the plasma, which rotates as a solid body underneath, and then with differential rotation in the convective zone. So there is a large shear in the velocity, and that's where it's believed that the dynamo is in action. And what happens is that the plasma pulls the magnetic field's flux tubes, and they end up rotating. And because the sun and the convective envelope rotates faster in the equator than it does at high latitudes, the magnetic field lines end up being more wrapped around the equator. That's the omega effect. And since the pressure inside the magnetic field ends up, the density of the magnetic field inside the magnetic flux tube ends up being smaller than the surrounding regions, it's buoyant. And what happens is that this magnetic field line, flux tube, will fluctuate to the surface of the sun and emerge. And in doing so, it can twist itself. And so what happens is, I'll just, okay. So for instance, here is a buoyant magnetic flux tube, which then can rotate, and that's the alpha effect, and can permeate or go through the photosphere. And in doing so, this is what happens here. So here's the surface of the sun, here's the convection zone. And so in doing so, it inhibits the radiative flux, or the convective, the transfer of energy from the interior of the sun to the surface. And so it's the temperature here at the foot points of these magnetic loops becomes cooler, and thus darker. And so those are the sunspots. And here's just an image in the ultraviolet showing magnetic loops, and here at the surface. Okay, this is another wavelength. So at ultraviolet X-rays, the loops are bright. In M dwarfs, so that's how the magnetic field is generated in solar-like stars with a convective envelope and an inner radiative envelope zone. But what about M dwarfs? Well, M dwarfs are a little bit different because you can have some late times, early M dwarfs, which are completely convective. And so what happens is that the activity of M dwarfs is higher than solar-like stars. And as you can see here, this is the rotation period. So and this is the ratio of the H alpha luminosity over the bolometric luminosity for different spectral types of M dwarfs. There's also known a relation of the activity with the age of the star, in the sense that young stars which rotate faster are more active than older star. And as the star ages, it loses angular momentum through a stellar wind, and in doing so, it rotates slower. So the rotation period increases with time. And here are like 3 examples of a fairly young star of 50 million years of age. And here is the brightness of the star. And what you're seeing here is the variation of about peak to peak of 10% in the brightness of the star. And then it decreases to maybe about 10% here, or not even that, 8%. And then maybe 1 or 2% here. And of course, these are artist impressions, but what we believe is that the young stars have much larger areas covered by star spots and rotate much faster. And here is just another way of looking at the magnetic activity and rotation. So here is the R, H, and K, a measure of the stellar activity. And here is the x-axis is could be understood as an age indicator. So, well, it's the observational rotation period divided by the convective turnover time. But you can see that for all these plots, here is the magnetic flux, and here is, I guess, this is the corona activity. So this is X-ray flux, and you can see that all of them decreases as the star ages. So there's clear relation that young stars rotate faster, have strong magnetic fields, and large areas of their surface covered by spots, and they're very active. In an M dwarf, well, this is just what I said. M dwarfs do not really fit the solar type relation. In M dwarfs, the activity is more prolonged, but anyway, the activity is a function of both age and mass or spectral type. So let's see, how do we characterize? How do we know this? So the first indicator that I'll talk about are the spots. So stellar activity. Then the spots, you can characterize the spots in themselves, their area, their intensity or temperature. You can measure the rotation of the star. You can try and infer the magnetic fields and also maybe the magnetic cycles. So spots. So here's just to show sunspots. What do sunspots look like? They have darker inner regions, which are called umbra, which have stronger magnetic fields surrounded by a penumbra, which are slightly brighter. Of course, current telescopes cannot measure star spots, no image star spot directly. But we believe that nevertheless, stars do have cool spots on their surface, just like the sun. There are basically three different ways of inferring the properties of star spots: Doppler imaging, photometric modulation, and planetary transit mapping, which was a method that I developed, was the first research to develop it in 2003. So here's Doppler imaging. You see the influence of dark regions with strong magnetic field on the surface of the stars on magnetic sensitive lines. And then you can map the stellar surface. So here are examples for a giant star, an evolved star, and here is the sun for comparison. And the photometric modulation is just that if you have a dark region on the surface of the star, or more than one, and as the star rotates, so when there's no dark features, you have maximum in brightness, and when this feature comes into view, the brightness decreases. And just as an example, here is Kepler 17, showing not only the transits, which are these periodic decreases in brightness, but if we just concentrate on the thicker line here, that's the brightness variation of the star due to the star spots on their surface as the star rotates. And the star Kepler 17 has appeared here over around about 10 days. And you can see that peak to peak, maybe it's about 3% variation. And here's the transit mapping, as I said, that I was the first to devise this method, was that here's the transit of the planet as the planet orbits a star, and if the geometry is such that there is an alignment in the sense that the planet will pass through the star and Earth, so we'll see a decrease in brightness, which is shown by this curve here. And this decrease is usually of the order of maybe about 1% for a Jupiter-sized planet orbiting a solar-like star, a sun-like star. But if there is a spot on the surface of the star, then what you will observe within the transit is a small increase here of about 0.1%. And this is, so we're looking in the transits for these small bumps. And here's just a simulation with the sun of a Jupiter-like size planet and an Earth-like size planet, which you can't even see, but there is a very tiny black circle here representing the Earth. And this is what the transit will look like when the planet crosses in front of a real sunspot. So here's the image of the sun. And so in the case of a Jupiter-like transit, this is what it would look like, with a decrease, as I said, of about 1%. In the case of the Earth, please notice that the transit depth here is 100 times smaller, is 0.01%. And of course, then the feature, the same spot, okay, will produce a relatively stronger feature. Okay, so here's the method that I developed, which is called an eclipse. So first it's a 2D image of a limb darkened star. The planet is a black circle, and then you calculate the orbit in each time. Look where the position of the planet, and you just add up all the pixels in the image to get and normalize, of course, to get the light curve. And the orbit is characterized by a semi-major axis, a period, and inclination angle. And what about if the same limb darkened star has spots? Well, then, and so here is just a star rotating with some spots, and then the planet comes across. And these are basically, you see these features on the transit light curve. And each spot is characterized by an intensity, size, and position, which is given by a longitude, whereas the latitude is usually fixed for orbits parallel to the stellar equator. And here's just an example for Kepler 17. So here is what the actual data looks like. And then if you subtract a model, which is this dashed blue curve here of a star without any spots. So if you subtract, you get the residuals, and then you can see very clearly 3 spikes, and each spike is a spot, which was modeled this way. So here's the star with the 3 spots, and then the red line is the fit to the model. This method has been applied to many stars of different types. Here you can see by myself and my group, the G stars, the K stars, the M stars. I want to mention that there are many other spots like the J-pop, the SOAP, and other methods of the same thing, making, like the same type of modeling with spots and transit crossing. So this is not the only model. Of course, there are many other models which are well published in the literature, but I'm just going to focus on this model that I developed. And so with this model, if you measure a spot on a different transit, then you can measure, the rotation of the star. And here's a paper where you can see that these are images of the sun taken 3 days apart. And you can see that the feature here, the spot feature, changes you see it at different times during the transit. And then this difference in phase will allow you to estimate the stellar rotation period. Of course, there are more complicated ways of doing it in the case of stars. But if you, in the case of Kepler stars, you have sometimes, like hundreds of transits, and you get the possibility of the planet crossing the same spot on a successive transit while the star has rotated. And you can look for these features here and estimate them. Doing an autocorrelation function, of the flux deficit, you can estimate the rotation period. Magnetic cycles, just like, and this was the theme of a master dissertation of my student Raíssa Estrela. And so here, this is the case of the sun. That was the first indicator of stellar activity, and basically just counting the number of spots on the stellar surface will give you plots like this. And she did the same thing for Kepler 17, which was observed for 4 years with the Kepler satellite, which is a solar, like a G-type star with about less than 2 billion years, half the age of the sun. And here is the number of spots that we counted, normalized for Kepler 17, and then phase folded here. We did a lumps cargo of this. And then we found this peak here at about 410 days. And then this is the light curve phase folded. So showing that, of course, this might not be the 11-year cycle, but might be a short cycle. The sun has quasi-biennial cycles. So this is probably not maybe the full activity cycle. There might be a longer cycle, but of course, since the observation was limited to 4 years, we can't really go past much more than that. But anyway, there is some kind of cycle at around 410 days. And she did the same analysis for Kepler 63, obtaining a similar value. Of course, what we want is a longer time baseline to be able to estimate longer cycles. So to summarize this first part of spots characterization, then we can measure short magnetic cycles. Didn't go through this, but we can measure magnetic field. If we do an analogy with sunspots, we can definitely estimate the spots characteristics and the stellar rotation and differential rotation. So now let's go into the second half of the talk. Well, I want to talk about stellar activity impact. So besides spots, what are the other features, phenomena, which can have an impact on what we call here on Earth space weather? So going back to the sun for an analogy, so when radiation and particles produced from solar events such as flares or coronal mass ejections, which are big chunks of mass which are ejected from the sun, tons and tons, and just go through space. And here, just for scale, here's the Earth and one of these coronal mass ejections, and also the radiation emitted during flares. So you can have lethal doses of X-rays for astronauts, alteration in satellite orbits due to drag close to near Earth, geomagnetic storms here on Earth once the magnetic field of these coronal mass ejections interact with the Earth geomagnetic field, then reconnections occurs and the global disturbances in the magnetic fields, ionospheric alterations, current peaks in transmission lights, blackouts, ozone layer alterations, auroras, and a more controversial long-term effect such as on the influence on Earth climate. But all of this would be the subject of a whole talk. So I'll just leave it at that. But what are the impact on exoplanets of stellar winds, coronal mass ejections, flares, and also the ultraviolet radiation, especially of young stars? Of course, in the planet side, they can cause the erosion of the atmosphere of the planet, as well as its photoevaporation through the UV radiation, and of course, affect habitability. So how do we know if such things occur on other planets? Well, if we look at transits, measuring these transits not on white light, but on X-rays and ultraviolet, what we see is that the transit depth at these wavelengths are usually much deeper than in optical wavelength. And so here are some examples showing, for instance, here is the regular transit, and then here would be the Lyman alpha or ultraviolet transit. And basically, and here is another example for three different, here is in X-rays and ultraviolet. And basically the idea here is that here's a planet and there is an extended atmosphere. And so this extended atmosphere of the planet, especially because these are close in orbit planets, that is, they're very close to their stars. So they're very hot with temperatures at the top of the atmosphere of the order of a few thousand Kelvin. So what happens is that, of course, these atmospheres are bloated or expanded. And then you have a larger projected area covering the star than just in white light. And this is just an artist's impression of what the UV radiation, which would photo evaporate the atmosphere of the planet, would look like. And here is an actual transit. So this is an actual transit. See, here is like not even 1%, right? 1% would be further deep. So this is the transit of something that would look like this, a planet with a dusty comet-like tail. And here was also a simulation of in ultraviolet of HD 209458, the first planet to be detected through transit. So this just showing that planets do have an atmosphere which is not only extended, but even sometimes you can see this effect of evaporation. Stellar winds. Okay, so here is results of MHD simulation. Actually, I think these are not MHD. I think these are particle simulations of the Kepler 11 system. So here are the 5 planets going from the closest one to the furthest. And you can see that the closest one would have, just because, and then the blue particles are planetary particles from the planet atmosphere, and red particles here are particles from a stellar wind of Kepler 11, of the star Kepler 11. So you can see that the closest in planet would get this, would form this comet-like tail and would have much more loss of its atmosphere than the inner planet. Excuse me, than the outer planet. This is the inner planet. This is the outer planet. And here was a study done by Yama of in the near ultraviolet. So these are the data, the crosses here. The green line is what would you expect just from a transit in the ultraviolet. And here are different models. And the difference here is that they model what it would look like if there was a bow shock in the near ultraviolet. So a bow shock due to the stellar wind. So this is what is represented in these lower images. And you can see that the model with a bow shock, and a bow shock is what you expect to form when there is, let me just go back here. So this is what the bow shock would be. It's where you have the shock between the stellar wind and the planet atmosphere. If I'm not mistaken, these models do not take into consideration a magnetic field for the planet. Coronal mass ejections. So these, as I said, were like these huge bubbles of plasma and magnetic fields which are expelled. In the case of the sun, we know it. We know that CMEs occur, and since the 70s, they were only observed once we had satellites to detect these. These are slow phenomena compared to flares. Usually CMEs take hours, to be deployed. And both flares and CMEs and spots, they all follow in the case of the sun, the solar activity cycle. So when you have a solar maximum, you have more sunspots, more flares, and more CMEs. And these are MHD simulations, 3D, showing the impact of the arrival of one of these coronal mass ejections on a planet. And here was considered a solar type wind with a CME. So what you can think of is like the solar wind is like this constant flux of particles, the stellar wind is this constant flux of particles that emanate from the solar corona. And then once in a while, you would have this bursts of bubbles of coronal mass ejections, which of course travel within, not within, but like travel through the solar wind is like a very large increase of the temporary increase of the solar wind. And of course, they also strip the planet of the outer. They can also strip the planet of the outer atmospheres, especially if the planet have no magnetic fields. And I would also like to call your attention to the work done by Aline Vidotto. And she has done many works on this, on stellar wind and coronal mass ejections. And so here's just as an example, a star with a constant, as I said, flux of wind. And here is a planet, maybe with a magnetosphere. And then it can either flare, or which is what I'll talk about next, or produce a coronal mass ejection. As far as stripping or erosion of the atmosphere of the planet with or without magnetic fields, the coronal mass ejection are much more efficient than flares. The effect of flares, and that's what I'll talk about now, is much more on the ultraviolet radiation. So super flares, as they are known, because they are about 1,000 to 10,000 times more energetic than the most energetic solar flares. That's why they're called super flares, have been observed on many stars by the Kepler satellite. Here is a survey done by Maya Hara in 2012, where they observed almost 10,000 solar type stars and detected 365 super flares with energies more than 10 to the 35 ergs in 148 stars. And here's just to show you the light curve of a star. And then these are, there are many smaller flares here, but then there's this huge flare here. And just to put you into perspective, here is the largest solar flares. And this is where the solar flare, the stellar flares range are. And of course you have the nanoflares and stuff, but they all seem to follow roughly the same power law of a slope of about a little bit less than 2. The frequency of flares depending on the stellar spectrotype. So M dwarfs are much more active. They flare more. This is just the flare frequency, okay? So young solar type stars have stronger flares than M dwarfs, but nevertheless, this is just the flare frequency. So M dwarfs, then K dwarfs, G dwarfs, and then sun-like stars, which are can be considered inactive if you compare it to the counterparts, like they're active, younger solar-like stars. So super flares on the sun. So, and now I'm going to talk a little bit about part of the work that was done by my PhD student, Raíssa Estrela, the same one which studied the solar cycle, the stellar cycles. And so could super flares have occurred in the sun, in the young sun? And of course, in the beginning, that changing the atmospheric chemistry and the ultraviolet light that arise with flares could be interesting for producing chemistry for the origins of life. And especially because the young sun it was only 70% of the brightness that it has today. But on the other hand, it can also be negative. So now I'll talk about the biological impact of these super flares of planets that are in the habitable zone. So the effects can be many, because during a super flare, you have an enhancement on the amount of X-rays, extreme ultraviolet and ultraviolet radiation. And of course, depending on the energy of the flare, this can cause changes in the atmosphere composition and also even photoevaporation and atmospheric loss. And the protons that arrive can also destroy the ozone. And so this could, in principle, affect the origin and evolution of life in a planet that was, like Earth, for instance, in the young sun. We know that we survived, life survived, and we're here to prove it. But anyway, how was it? So the goal of this work was to determine if superflare, how dangerous were superflares to life present on the Earth, on the surface of or on the ocean of a terrestrial planet. So first of all, we chose the Kepler 96, which presented 3 superflares. And the Kepler 96 is orbited by a super Earth, a close-in. It's not in the habitable zone. Its surface temperature is estimated to be about 2,000 to 3,000 K. And also, we also applied it to the TRAPPIST-1 system, which has 3 planets in the habitable zone. But in the case of Kepler 96, we considered a hypothetical planet in the habitable zone. And Kepler 96 is very much like the sun. But the only difference is that it has twice the age. Its age is estimated to be about 2.2 billion years, and that's exactly when the first multicellular life forms arose on Earth. So here's basically the outline of the work. So we measured the flare and the optical using the Kepler satellite or the K2 mission in the case of the TRAPPIST-1 system. We use as proxy of the star in the case of Kepler 96, the sun, and in the case of TRAPPIST-1, the 80 Leo, for what? To estimate the amount of ultraviolet, the percentage of ultraviolet light, the radiation produced with that, produced by that flare that is measured in the optical. If in the case of the Kepler satellite, we didn't measure the flare in the ultraviolet. And as for the planetary atmosphere of the terrestrial planet orbiting Kepler 96 and TRAPPIST-1, in the case of Kepler 96, is the hypothetical, we consider 2 types of atmospheres. A present-day atmosphere with ozone on it, and an Archean atmosphere, which is the case of the atmosphere that the Earth had, and when it was about half its age, and which had no ozone, because the first algae hadn't started producing the ozone, the oxygen. And then we estimate, depending on the type of atmosphere, how much ultraviolet flux will reach the surface, and then the biological impact on 2 types of bacteria. The Deinococcus radiodurans, which are the most radio-resistant bacteria that we know here, an extremophile that we know here on Earth, and Escherichia coli, which is a very common type of bacteria, which we all have in our guts. And that's I said it before. So why Kepler 96? As I said, it corresponds to the age of the Archean era on Earth. That's when it had the great oxygenation event, which the first algae started to produce oxygen, and we had an increase in the oxygen in the atmosphere, which allowed the formation of the first multicellular organism. So here are the 3 flares, and they all the 3 flares were detected during transit of the Kepler 96b. And here, I'm just going to focus on, we estimated for the 3 flares, but I'm going to focus on this stronger flare, which is about 1.810 to the 35 ergs, which correspond to a super flare. And again, here, what is the difference of in the atmosphere? Here's how much flux. So here's the flux. The solid lines are the flux at the top of the atmosphere, and how much of this, and here's in the ultraviolet wavelength, and how much of this flux reaches the surface of the Earth according to its wavelength. If the atmosphere is of an Archean type, that's the green lines, or present day with ozone. And the difference here, the solid line is the constant value or the continuous value, and the dashed line is how much of the ultraviolet radiation is enhanced due to the flare. And so here's basically the composition of the Archean atmosphere. It's both of them are 80% nitrogen. The difference here is that the present day is 20% oxygen, whereas the Archean atmosphere is 20% carbon dioxide. And as I said, in the case of the strongest solar flares that we had measured, or one of the strongest one, I think it's the second strongest one, in 28th October 2003, we measured that 12% of that flare would be, of that energy of that flare was in the ultraviolet. So if we extrapolate to the case of the super flare, we would have an increase of 5,400% increase in the ultraviolet flux. Okay, and in order to estimate the biological impact, we need something which is the action spectrum of the bacteria, and each DNA has a different action spectrum, which is the relative response of that organism to this, to the UV flux. And we know that the DNA is mainly damaged in the ultraviolet, the C and B, UVC and UVB range, which are for wavelength smaller than about 300 nanometer. And so here is the result. And what we know is that the maximum flux dosage that each bacteria can support for 10% survival, that is a flux larger than 553 joules per square meter, will kill 90% of the bacteria in the case of the Deinococcus radiodurans. And for the case of the Escherichia coli, 22.5 joules per square meter is enough to kill 90%. So we estimated the effective irradiance reaching the surface to estimate what the flux would be. And so that's for no atmosphere, it's huge. And then for an Archean atmosphere without the ozone, which absorbs a large part of the ultraviolet radiation, fortunately. Nevertheless, in the case of the largest, remember there were 3 flares, the largest one, it's way above this limit here. But with a present day atmosphere, so if at that time in a hypothetical planet already had ozone, then the 2 bacteria would be safe. For the smaller flares, the same thing. And Deinococcus radiodurans this is about less than half, a little bit over the half of the maximum dosage. So here, if we consider this very large flare, only with ozone, the bacteria could survive. Okay, so we know that here on Earth, if the sun was like Kepler 96 and produced such strong flares, then there also happen strong flares. And we know the life did thrive and survive and thrive. So then we decided to estimate, well, okay, what if life wasn't on the surface of the planet? Or the life on the surface would be sterilized by such super flares. But what about if we also had life, within an ocean or a lake protected by layers of water? So we estimated what would be the minimum ocean depth, which would absorb the ultraviolet radiation from such super flares. And we did that for both bacteria, for the largest super flare, and we estimated that bacteria such as Escherichia coli would be safe if they were deeper than 28 meters. And for the case of Deinococcus radiodurans, these bacteria would be safe if it were until 12 meter. If they were like above 12 meter on the surface, they would be killed by the ultraviolet radiation from the super flare. But if they were below that level, then they would be safe. The water would absorb most of the ultraviolet radiation. And this work was published in Astrobiology journal in 2018. For the TRAPPIST-1 system, which is an M8 red dwarf, we did the same thing because it has 7, it's a cool M dwarf, and it has 7 terrestrial planets, 3 of them in the habitable zone. It was observed by the K2 mission for about a month, and 47 flares were detected. Flares between 10 to the 30 and 10 to the 33 ergs. Remember, this is an M dwarf. It's a smaller star, but it flares much more. And 10 to the 33 is already 10 times stronger than the strongest flare that the sun produces today. And here, just to show you, is the example, the time profile of the strongest flare. And we did the same. And here's the same thing for the Archean, for the present day without ozone and the Archean atmosphere. And here showing the difference between how much flux arises at the surface with or without flares. But we went a step further than the work we used the atmosphere model of O'Malley and Kaltner, and we went a step further than what we did with Kepler 96, in the sense that we did use the Géant 4 code, which is a sophisticated code which takes into account radiative transfer and so on. And we estimated the ultraviolet spectra of the flare on the surface. Here is on the top of the atmosphere, and black is just the sun and the flux at Earth. And here, of course, there it's higher because the planets, it's a much smaller system because it's an M dwarf. So the habitable zone is much closer to the star than the habitable zone of the sun, which is at roughly at 1 astronomical unit. It's much inner. It's smaller than the orbit. The whole system is contained within the orbit of Mercury. And so here is these are for different times. So the red curve here would be at the peak of the flare. And you can see for an atmosphere with ozone and an atmosphere without ozone for the 3 planets and how much flux. Here's for an Archean, and here for an atmosphere with oxygen or ozone for the 3 planets. And this work was published in Astrobiology last year. And the result was, again, that for an atmosphere with ozone, then you would have no problem for the bacteria to survive. But in an atmosphere of Archean type without ozone, all life on all of the 3 planets would be, the surface would be sterile because the ultraviolet from these super flares would completely kill eliminate the bacteria. And, but of course, I mean, for both these planets raises the question, but for you to have ozone in the atmosphere, you need life, you need living organism, through photosynthesis to produce the oxygen, which will then produce the ozone layer. So it's you have to produce life. Life has to produce oxygen somewhere within the planet. And again, well, maybe not on the surface. On the surface, it doesn't seem possible, but maybe in, oops. Oh, there's a slide missing here. I'm sorry. But again, we also did the same thing where we calculated how much the layer of water in the ocean where these bacteria could survive and the impact of the ultraviolet impact of a super flare. And again, we also got like a few 10 to 20 something meters below the surface of an ocean, or in the case, could also be a lake. Okay, so to conclude this part then, so the activity, the stellar activity can impact life on an orbiting planet in the form of ultraviolet radiation, which can photoevaporate the atmosphere, and that would be like young stars which have strong ultraviolet radiation, which would cause the evaporation of the atmosphere. Wind can also pick up the ions and also erode the atmosphere of closing planets. coronal mass ejections are enhanced, just would enhance the effects of winds in the sense that they last for hours. It's like this huge concentration of particles and magnetic fields, which can also cause loss of atmosphere. And the last part, which I dwell a little bit longer on, the impact of flares and their ultraviolet radiation on possible living forms which exist on the surface of the planets. And what I showed you was that ultraviolet radiation from super flares, I mean, even the most extremophile, which can survive ultraviolet radiation, high dosages of ultraviolet and X-ray radiation, which is Deinococcus radiodurans, could not survive on the surface of planets if there were no ozone layer. And of course, in the beginning, there weren't any ozone layers, so probably life, which is what we believe happened, we know happened here on Earth, started in an ocean or in lakes. And then once the oxygen, there were enough oxygen on the surface to produce an ozone layer, then life could go to the surface of the planet and be protected from the lethal ultraviolet radiation. And so what next? So here are 3 topics which PhD students of mine and candidates candidates for a PhD are working on, which is the planetary atmosphere evaporation due to stellar winds of the TRAPPIST-1 system planets. There are 7 planets for us to simulate. The effect of the stellar spots on the transmission spectra of exoplanets. So now, especially with the James Webb Telescope, a very promising topic is doing transmission spectra to try and characterize the atmosphere of exoplanets. But the thing is that, of course, the transmission spectra depends on what the surface of the star looks like, what is emitting. So what is the effect of the spots, which we're going to see on the transmission spectra. And again, the study that I presented you was the impact of just one flare or a single event. But we know that for those stars, and especially for the M dwarfs, there are many flarings, more than one flare per day, more than one flare super day. So what is the impact of like simultaneous flaring, like with a high cadence of ultraviolet radiation on life forms? Of course, this is going to be more harmful than just a single event, because then maybe the bacteria won't have time to recompose itself. Okay, and that's it. Obrigada, thank you. And I'll just want to point out that the Eclipse code is available in IDL or Python, publicly available. So thank you.
Thank you, Adriana. Very nice talk. We have a lot of questions for you here in the YouTube chat.
Okay.
First question that I took note here was from Ricardo Gando, but I think that it was already answered in the Q&A chat. I'm not sure if Ricardo wants to ask it again, or if it was replied. So Ricardo, if you want to speak, you can open your microphone or you can write it in the chat. Otherwise, Marcelo has a question.
Bia, I think there are questions from Jean Questing and also Claudia Laggio. They can go first, please.
Okay.
Okay, can you hear me?
Yes.
Yeah, Adriana, I liked your talk.
Thank you.
The sun was active during the Archean. There were flares, and but life, we think, got started by 3.5 billion years ago or earlier. So it did make it through the flares without any
Mhm.
ozone layer. So what is your explanation for that?
Yeah, that's why we went for Kepler 96, and we did that simulation or that modeling within water, so below water, so ocean or lakes, and that's where, if I can. So exactly, that's what we know, that life did survive super flares on Earth. So here's the calculation that we made, where water would absorb this ultraviolet, this extra ultraviolet radiation from flares. And we estimated this minimum depth for both bacteria. So
there are also a couple other ideas that have been suggested in the literature. One is that stromatolites, mat forming organisms that form layered stromatolites might protect themselves from UV. That was something that Lynn Margulis, I think, suggested 40 years ago or so. Also, in some of our models of the Archean atmosphere, if we have enough methane, we can form an organic haze like you see on Titan. So that might be another way of shielding against UV radiation.
Okay, that's true. Thank you.
Thanks.
Thank you. So Claudia, do you want to, I saw you wrote a comment on the chat. Maybe you want to.
Hello.
Hi, Claudia.
Hello, Adriana. Nice to see you in such a good health.
Nice to see you.
Okay, so I wrote just some comments on the chat, and mainly regarding the need of Deinococcus radiodurans for oxygen, because it's extremely aerobic and anaerobic microorganism. So I strongly suggest to include an anaerobic microorganism in your calculations, because there are ones, but they should be more targeted to your model in terms of your calculations and simulations.
Okay, that's true. Okay, thank you, Claudia.
Thank you.
You're right.
Okay, thank you, Claudia. I think Marcelo now can ask his question.
Okay, thank you so much, Adriana, for this very nice talk. My first question is simple. Could you talk about a little bit about Proxima Centauri? Are the conditions there similar to TRAPPIST-1, do you think?
What is the age of Proxima Centauri?
I have no idea.
Well, even though, I mean, the M dwarfs don't follow that closely the activity age relation. I don't know. I'll have to check if Proxima Centauri produces flares, because that's another student of mine, a PhD student who should finish by the end of the year. He is really working on why some very spotted stars with strong active Gustavo just said that it does flares a lot. But anyways, what I was just going to say, just to finish what I was going to say, is that there are stars which are very spotted, have strong, have strong spots and influence, but do not produce flares. So what is happening? There are young stars with lots of spots, but no flares. So that's something that we are trying to see what might be going. But yeah, Gustavo said that it's about the age of the sun, 5 to 6 gigayears, a little bit older than the sun, and it does flare a lot. So in principle, I guess we could do the same study, of course, with improved improvements that were mentioned here by Claudia and James Castor.
Okay, great. And I have another question is concerning, for example, the young solar system, when the sun had some super flares, for example. So do you think that, for example, for some moons around giant planets, for example, the moons of Jupiter, they could keep some habitable conditions, even considering the presence of super flares? in this scenario, do you think?
The thing is that here we didn't consider that the superflares would heat the atmosphere, but rather that they would momentarily enhance the dosage of ultraviolet flux. So it'll be like a burst of course, I mean, it's going to be like, I mean, the flare produces radiation in the whole electromagnetic spectrum. But here we're just considering this burst of ultraviolet radiation, which is harmful to DNA. I don't think flares could heat and thus, you know, like produce habitable conditions.
Okay, thank you,
Because
Adriana.
it's just it's sporadic. It's too sporadic.
Okay,
but it can cause a great damage, you know, like in the DNA. It can sterilize.
Okay, thank you so much.
Thank you, Adriana. I don't know if there are any more questions here in the chat of Zoom. If people can write on the chat if they want to ask something to Adriana. In the meantime, I have a question regarding the transit mapping method that you presented for the stellar spots. So you have this signature in the light curve, right? That can tell you about the spots. And what would be the main, I mean, gravitational effects that could, perturbations, let's say, that could mimic the same effect, the same signature in the light curve, like maybe other planets or other or exomoons or something like this. Could this signature be mistaken for a sunspot, but really mean something else?
I mean, we have done many simulations of also of exomoons, but the effect is different because for spots it goes up and down. Because the moon also transits, what you see are things more like step-like function. So, for instance, if there was an exomoon, it would go like this, and then it would go down. So, I mean, they last longer than the features from the spot. We've done many simulations with exomoons, so they are different. And again, and it's the same thing of because an inner planet from Kepler's law would have a faster period. So, I mean, an outer planet with an inner period, I mean, they would both go not together, but you see, it's not something like this. For it to be something like this, it has to be something which is moving with the star. And so
okay,
not that fast. And
okay,
usually an inner planet would move faster than an outer planet, which let's say one would eclipse the other. And there are many systems where you can see the double eclipse. You know, one planet starts transiting and then the other comes along. And then you have like these oddly weird shaped transits. But the main thing here is that moons or other planets will cause longer lasting signatures on the transit light curve.
Okay, thank you. So I think we can start with the questions from
Bia.
YouTube chat.
Bia, sorry, I think Renato has a question.
Oh, sorry, Renato, please.
Okay. That's okay. So I had actually a couple of questions. Very nice talk by Adriana. Very, very interesting.
Thank you.
One is more planetary. You mentioned that that one of the impacts of the lack of magnetic field would be the evaporation of the atmosphere of the planet. And I was wondering if the models actually show this in an ubiquitous manner, because Venus has no magnetic field and has a very thick atmosphere. And the second question, which is I think way more biological, is that I thought was very nice, the idea of seeing how deep an ocean would have to be to get, either by the effect of lack of magnetic field or solar flares, how deep could bacteria survive? I'm just a little concerned that basically the radiation is just a selective pressure. Maybe that's a question for biologists in general. So here on Earth, you have tardigrades that can rebuild their DNA, and you have sponges that resist radiation a lot. And this may not mean the boundaries, right? If you have an environment where you're continuously bombarded by radiation, so this would be a selective pressure to favor organisms that could survive that. And so those are my two remarks.
Okay. Okay. Yeah, I would rather, because these are much more on the biological side. So maybe Claudia can comment a little bit on it. But yeah, I really, I agree with you, but there's not much that I can add to it. So I don't know if Claudia wants to say something. Yes.
Oh, okay. So if there are not any other questions, we can go to the chat from YouTube. So our assistants will start reading the questions for you, Adriana.
Okay.
Hi, Adriana. I'm Raquel. It was such a great talk. Congratulations.
Thank you.
There were some questions from the YouTube chat, and I'm gonna read the first one. The Victor Erivelton de Souza Silva asked, how are the detections and analysis of elements that indicate life on other planets made?
Ooh, okay. Well, first of all, we haven't identified yet any life, any indication of life on any other planet so far. And the searches right now are in the sense of looking for the presence of oxygen or ozone in high quantities, because a little bit of oxygen is okay. You can produce it from non-biological sources. But and that's where the transmission spectrum comes in, where what we plan to do, especially with the new telescopes, like the James Webb telescope, which is going to be launched in December this year. But probably I don't think James Webb will be able to characterize terrestrial planets anyway in the habitable zone of solar-like stars. But nevertheless, it's going to try and characterize the atmospheres of terrestrial exoplanets. And the holy grail here is to detect oxygen or ozone, which I guess has stronger features. So yeah, water vapor has been detected in the atmosphere, even of giant planets has been detected. So.
Thanks.
And of course, there's the whole, let me mention also the SETI program, the extraterrestrial intelligence, the search for extraterrestrial intelligence program, which searches for radio signals from an intelligent civilization. But that's, then we're just waiting for that. And it's a program that started in the 60s. So it's been over 60 years. And so far, no signal has been verified.
Thanks. I hope Victor got satisfied with your answer.
Hi, Adriana. Good morning.
Hi.
My name is
Luis Felipe.
My name is Luis Felipe Menezes, and I'm going to read the second question from YouTube. It's from Thiago de Mello Santiago, and he says, I have read in some papers that there are some theories trying to explain star magnetism. It seems the dynamo theory is more accepted. Is it true?
Yes, yes. There are different types of dynamo, but yes, the magnetic generation of magnetic fields is, I mean, this is something like from Faraday, right? It's something that it's not only magnetic fields of stars. Magnetic fields are generated by dynamo. So yeah, that's the main theory. Mm-hmm.
Okay, thanks.
And there are different types of, again, there are different types of dynamo. Solar-like stars are the alpha omega dynamo, but there are other mechanisms which have been proposed for M stars. Mm-hmm.
Okay, thanks.
But still dynamo, it's still dynamo, which is the current movement of charged particles such as electrons will produce variation of charge currents will produce magnetic fields. And that's something that you can do at home.
Okay, thank you.
Hello, Adriana. Good morning. I'm Marcos
Vinicius.
And first of all, great lecture. Thank you very much. Very informative. And I've got a question here from YouTube. It comes from Jorge Carvano. And they say, planets in the habitable zone defined by temperature around M stars tend to be very close to these stars.
Mm-hmm.
Since M stars are so active, is there any hope of these planets actually being suitable for the emergence and development of life?
Yeah, well, and that was the goal when we studied the TRAPPIST-1 system, because it's exactly such a system. It has 3 planets in the habitable zone around a very active M star, and the planets are very close in. They're even the ones which are in the habitable zone. And again, oops, too fast here. So these are the results for the 3 planets, TRAPPIST E, F, and G, which are the 3 planets in the habitable zone. And here would be the contribution of the strongest superflares. So again, following the same line of thought, if initially life developed in oceans or lakes, or like in shallow waters, it doesn't even have to be very deep, then first of all, and then produce, of course, I'm talking about life as we know on Earth, life forms like, with photosynthesis, which would then produce oxygen, and this oxygen would recombine in the atmosphere to form an ozone layer, which would then block or absorb most of the ultraviolet radiation from flares. Then, as you can see here, the life forms on the surface would be okay. And again, just also it can be water, but it can be like James Gaston mentioned in his comment, like the what's the name of that? Which, they're like coral-like structures, so they're protected, but like a layer of, I don't know if they're made of calcium or whatever it is. What is it called again? Stromatolites. I'm sorry, I forget now. But again, it's not just water; it's another kind of. And an initial undergraduate student of mine from the who is biology, and he was trying. He has a project to study, for instance, in the case of Mars. What about if life forms were in caves, or, well, maybe not caves, but like under rocks, because that can also block the ultraviolet. So he needs a protection from the ultraviolet flood radiation.
Thanks.
Hi again. Another question taken from YouTube was made by Eduardo Machado Pereira. He first says that thanks for the great talk, Adriana. Are M dwarfs also subject to magnetic cycles? Since the tachocline helps twisting magnetic field lines, how would this take place in fully convective stars?
Oh, from the top of my head, I don't know about, because I mean, solar-like stars, yes, they do have magnetic cycle, which is the Mount Wilson program, which has over 50 years of length now. But I don't know. I must confess that I haven't followed the literature on M dwarfs activity cycles. So I'm sorry. I'm not saying that they don't show it. I'm just saying that I don't study that, so I don't know. So I don't know if any of the astrophysicists, stellar astrophysicists here, if you could help me. Gustavo just mentioned that he's not sure any cycle has been identified in any M dwarf. So yeah, I don't recall, but it's not something that I follow. So I'm sorry. The answer is I don't know.
That's fine. Thank you very much.
Thank you, guys. Raquel, Vinicius, and Luis Felipe, do we have another question?
Again, we have one more question from YouTube. It is from Thiago Madruga. And he says, good morning, I'm a science teacher, and I'm highly grateful for the remote transmissions made by Observatório Nacional. This democratization of the access to information is very important. Last week, I was talking to my students about SETI. One of them raised the issue of the long travel time of the signals, round trip, to establish a communication. So what?
Well, yeah, you have to be patient. It's true. I mean, the nearest star, which is Proxima Centauri, is a little bit over 4 light years away. So yes, any radio signal will take 4 years to arrive and 4 years more to go back. So you have to be very patient and wait at least 8 years for an answer to from your signal. That's true. But SETI is not interested in communicating. It's interested in detecting signal. For instance, what you can think of is like all our broadcasts of radio signals, like from the radio, AM and FM, and from TV, all these TV signals, which are just broadcast. I mean, they're broadcasting to space. So maybe if there is some intelligent civilization in the planet around Proxima Centauri, and if they have the ability, they have constructed radio antennas and detect our signal, they're going to detect, like what we broadcast 4 years ago, the musics, the TV series and whatnot. So that's mainly what SETI, the aim of SETI, is not to establish a back and forth communication. I mean, not that it's not possible, but you will have to be patient because it will take at least 8 years for the signal to go back and forth. And of course, for more distant stars, even longer. But we don't have to wait for that. It would already be tantalizing for us to just detect the signal from another civilization. Okay, it doesn't mean they're not out there. Maybe they're not interested in radio antennas. Maybe they're way past that, like that's in their distant future, distant past. And now they're moved on to other types of communications. Yeah. Like cable internet. But once we start with cable internet, right, we won't be broadcasting anymore TV signals.
Okay, thanks. I believe this was the last question. Yes. So thank you once again, Adriana.
Well, I thank the Observatório Nacional, Marcelo, Borges, Beatriz, and all the organizers.
Sorry, Adriana, sorry. There is another question here. I think Luis mentioned the last question from YouTube, but there is a question here.
I'm sorry.
From,
okay.
No, it's okay. From Eduardo Janot Pacheco.
Okay.
Do you want me to read it, or will you?
Oh, yeah, you can read it.
Okay, very rich talk from the astrobiological point of view. What do you expect from the Plato mission, from the kind of research you're doing?
Oh, well, definitely Plato will be the next planet hunter, right? Well, as you know, I'm also part of the Plato team I'm in charge of actually estimating the rotation period of stars using this transit mapping, this method that I mentioned here. But of course, what Plato will probably do is it will detect, hopefully, dozens, maybe more, of Earth-like planets or terrestrial Earth-like planets in the habitable zone of stars. So I think that will be the major contribution to Plato to astrobiology, will be identifying the planets which are terrestrial and which are in the habitable zone. And of course, if for a long enough mission, it will be able to identify longer period planets, not just the close-in, because I mean, all of this that I mentioned today, of course, the effect is much worse if it is a planet very close to the star, right? Because then, of course, the radiation, the flux, the wind, the CMEs impacts, everything will be much more, will be stronger if it's much closer than if it's further out. And so in the fact that, so I think that would be the main contribution of Plato, identifying candidates for habitable planets. And of course, characterizing and doing other. Oi, Janu. Hello, Janu. Good to see you.
Thanks for the propaganda. Thank you.
Okay.
Bye.
Okay, thank you, Adriana. So this really was our last question.
Oh, okay.
Thank you so much for your talk.
Well, I'm very grateful for having this opportunity, and thank you very much. And I hope to be able to attend the next Astrobio from ON in person next year. Even if not that I need to give a talk, but just to be there and attend the lectures, which I'm sure
waiting for you, Adriana.
Okay. So thank you very much. Thank you all for listening.
Thank you.
Bye.
Thank you so much,
Goodbye.
Adriana. So I'd like to ask the people to come back at 3 p.m. Brazilian time for the next talk that will be given by Dr. James Casting. Okay? See you there.
Okay. Bye.
Bye-bye.